So these are all the important problems that can be solved under this iterative improvement algorithm design technique. One is the simplex method. Second one is the uh, maximum flow problem or Ford-Fulkerson algorithm. The third one is maximum matching in a bipartite graph. The fourth one is stable marriage problem or Gall-Shapley algorithm, local search heuristics. In this video, we are going to discuss about how to find the maximum flow in a network. Maximum flow problem. So what is a maximum flow problem? So a problem of maximizing the flow of a material through a transportation network. Example, the pipeline system or communication or transportation network. Okay. So if you have to carry a one data from source node to destination node, say in the case of a network system or in a communication system. So we may not aware of that when you are forwarding a packet or a data from source to destination, it may go on a different way or the path where it is available, isn't it? So each and every node will have some capacity. Okay, in the source node you are sending some size of packet. Okay, so it may be passed on to the some intermediate node before reaching into the destination. No, and also you should know that what may be the capacity of the node. So each and every node may pass the data according to its capacity. So from node 2 to node 3 you can able to transfer only 2 Mbps. Okay, so you cannot pass the data or forward the packet which have more than that size. Okay, so accordingly it may be divided and it will reach into that destination. So that is an example of the maximum flow problem. So you have to transfer some material that can be of anything. Okay, for example, if you consider the water pipeline also, if the capacity is having the flow into that pipe is only this some 1 liter. Okay, so you cannot force more than that capacity into that pipeline. Okay, so our aim is you have to transfer the material or pass the material from the source to destination. Okay, in such a way that you have to maximize the flow. So how can you model this problem? In the sense, you can represent this Maxflow problem as a connected weighted graph with n vertices. Okay, with the following properties. Okay, so it has to contain exactly one vertex with no entering edges, that we call it as an source. Okay, and it contains only one vertex with no leaving edges called the sink. So that's what you have to send the material from source to destination. Then each and every edge will have some positive integer weight that we call it as an uij. That's what I have said. Each and every node will have some capacity. Okay, so uij is nothing but then the capacity on that edge. So that is only that much flow can send from the node I to node j. Okay, that we call it as an edge capacity, indicating the upper bound on the amount of material that can be sent from the node I to node j. So you can model this problem as an one connected weighted graph. So this is an example of a flow network. So here you have some 6 nodes. Okay, so you know that the source is a vertex which doesn't have any incoming edges. So we marked the node 1 as a source. Okay, then whereas 6 is the sink, the node which doesn't have any outgoing edges. There is no leaving edges from this node. So we mark this 6 as a sink. Okay, so the max flow problem is you have to maximize the flow from the source to destination. Then you have to find out the path where you can maximize the flow. Okay, or how much flow can be transferred from source to destination. Okay, where this edge weight between 1 and 2 represent as a 2, which is nothing but the edge capacity. So this much flow only can be transferred from node 1 to node 2. That is the meaning of this edge weight that we call it as an edge capacity. Definition of a flow. Yeah, flow is an assignment of real numbers xi j to edges ij of a given network that satisfy the following. So that is, you are assigning some real numbers on that edge I comma j, that we call it as an xij. Okay, it's going to be one real number. Okay, there is some constraints on that flow. It has to satisfy flow conservation requirements. What is the flow conservation requirements? Is the total amount of material entering an intermediate vertex must be equal to the total amount of the material leaving the vertex also. Okay, suppose if the two is entering into that thing, so the same has to be out. Okay, so that intermediate vertex cannot have an rights to add the flow or decrease the flow. Okay, so xji is equal to sum of xij for I is equal to 1 to n minus 1. Then next, capacity constraints. Okay, so obviously that is the flow should be less than or equal to capacity of the edge, and automatically it should be greater than or equal to 0. Okay, that is the capacity constraint. So this is your current flow. This is the capacity of the edge. So always the capacity should be greater than 0 and it should be less than or equal to this capacity. Next, what is flow value and maximum flow problem? So what I said, since no material can be lost or added to by going through the intermediate vertices, the total amount of the material leaving the source must be end up at the sink. Okay. So that is summation of x1j, this is a source, okay, equal to xjn, that may be the sink. So it may pass on to the sum of the intermediate vertices also. So the value of the flow is defined as the total outflow from the source. Okay, that is the total inflow to the sink. So what is the maximum flow problem is to find a flow of the largest value for a given network. The maximum flow problem can be considered as an LP problem also, that is linear programming problem. So the our objective is you have to maximize the flow. So maximize V is equal to summation of x1 j. Okay, so where 1 comma j is belongs to an edge. Okay, so the constraints we have already discussed, that is one is the flow conservation constraint and another one is the capacity constraint. So the flow conservation constraints, that is the flow entering into the edge should be equivalent to the flow leaving of that edge also. So the entering minus leaving, if you subtract, obviously we'll get it as 0. And also this current flow, it should be greater than 0 and it should be less than or equal to the capacity of that edge. So next we'll discuss how to find the maximum flow by using the algorithm called shortest augmenting path algorithm. For the shortest path augmenting algorithm, you have to find the augmenting path. Okay, then you have to adjust the flow on this path. Okay, find the shortest augmenting path, and that path we have to adjust the flow. So we will discuss first what is a flow augmenting path. So to find a flow augmenting path for a flow X, consider path from source to sink in the undirected graph each many two consecutive vertices I and j either. Okay, so there may be an two edges, forward edge or another one is the backward edge. Okay, so connected by a directed edge I to j with some positive unused capacity, that is residual capacity, Rij is equal to Uij minus Xij. Okay, so if it is a forward edge, you have to find out what is the unused capacity, that is still how much flow that can be sent on that edge. So the capacity minus current flow. Okay, we call this as an forward edge. And sometimes we'll have backward edge connected by a directed edge j to I with a positive flow xij, known as a backward edge. Okay. So the residual may be this: the minimum of Rij on all forward edges or xij on all backward edges. So you have to find the residual for this forward edge, whereas you have to consider the current flow as an flow that can be passed on that backward edge. Okay, for the backward edge you are not supposed to calculate what is the residual. So that is called as an augmenting path. So now we have to find out the shortest augmenting path. So how we are going to find the shortest augmenting path is by using some BFS, breadth first search manner. Okay. So starting at the source, perform BFS travel by making a new unlabeled vertices with two labels. Okay. So each and every, that is in order to find the shortest augmenting path, while you are entering the next vertex, we have to label each and every vertex. The label have two parts in it. One is the first part of the label. What is that? Second label. The first part of the label indicates the amount of additional flow that can be sent through, that can be brought from source to the vertex being labeled. Okay, that is how much flow you can send on that edge. That is the first label indicates. The second label value, what it is going to indicates that the vertex from which the vertex being labeled was reached. That is from which vertex the flow is entering. Okay. The next you have to mark with that either the positive or negative. So what I told for there may be a forward edge and negative edge. So if it is a forward edge, you label with the positive one. If it is a backward edge, you label with negative. Okay. Whether the vertex reached via a forward or a backward edge. So repeat, each vertex can be labeled with two parts. The first part of the label indicates the amount of additional flow that can be brought from source to that vertex being labeled. The second part of the label indicates the vertex from which the vertex being labeled was reached, from which vertex that is going to be reached, with the plus or minus sign, which indicates whether it is a forward edge or it's a backward edge. Okay. So now we'll discuss how to label this. Okay. So first, always you have to label the source vertex with infinity, comma, minus. So infinity means we have already know that source is a vertex which doesn't have any incoming flow. Okay. So that the first part of the label indicates infinity, there is no incoming flow. The second part of the label I have told from which vertex the flow is the flow is entering. Okay, so since it is a starting vertex, there is nothing. The remaining vertex has to be labeled. Okay, as follows. So first you have to label the forward edge, next you have to label the backward edge. If any unlabeled vertex j is connected to the front vertex I of the traversal q by a directed edge from I to j. So that is if you have an edge I to I to j, that is if it is a forward edge, you have to label this vertex. You have to label this vertex, that is positive unused capacity Rij equal to Uij minus Xij. So here it is a one edge, no. Here you will have some capacity and as well as current flow. Capacity minus current flow. Okay. Then vertex j is labeled with Lj comma I plus, where Lj equal to minimum of LIR comma RIJ. Okay, so RIJ what we have find out. Okay, so suppose you are going to label this vertex. Okay, then you find out what is RIJ. So you have to label with LI. What is that? The current flow can be added on this edge is nothing but the minimum of Rij and this flow of this vertex. Okay, whichever is minimum, that you have to be labeled. That is the thing. Okay. The second part of the label indicates what I told, from which vertex the flow is coming. Okay. You label with that vertex number. If it is a forward edge, you label with plus. Okay. The next, you have to label the backward edge. If unlabeled vertex j is connected to the front vertex I of the traversal q by a directed edge from j to I with a positive flow ji. So you, in order to label the backward edge, you don't consider the residual, just you consider only the current flow. Okay, vertex j is labeled with again the current flow or this flow of this vertex, whichever is minimum, you have to label it. Okay. So this is the first part. What is the second part of the label? From which the flow is entering. Since it is a backward edge, you have to label with minus. So once again, I'll repeat. Each and every vertex will have the two parts of the label. The first part of the label indicates how much flow that can be added onto that path. Okay. Second part of the label indicates from which vertex the flow is considered. If it is a forward, you label with the plus. If it is a backward, you label with minus. Okay. Source is always labeled with infinity comma minus. You have to label the forward edge by finding the residual capacity minus current flow. Then you have to label with the minimum value. So whether this Rij or this Lj, I plus, which is having this minimum value, that has to be labeled with Lj, comma I have told you, the second part of the label, from which vertex the label is, the vertex is reached, plus, since it is a forward edge. So for the backward edge, you have to consider only the current flow. So you label that vertex minimum of Lj or Xji, whichever is minimum, okay, comma I minus. So I is nothing but from which vertex the flow is coming. Since it is a backward edge, you label with minus. So that is I told forward edge, you have to use this residual. Backward edge, you have to use only this current flow. So once if you have labeled all the forward edge and the backward edge, okay, you have to check if the sink has been labeled. If the sink, which means that you are finding out the shortest augmenting path, you are supposed to adjust the flow. So if the sinks ends up being labeled, okay, the current flow can be augmented by the amount indicated by the sink's first label. Okay, I'll repeat. First you will label the source vertex. Next you labeled all the forward edges. Next you have to label all the backward edges. So you have to continue like this since all the unlabeled vertexes has been labeled. Once if you have labeled the sink, you stop the labeling process. You have to check whether the vertex has been, sink has been labeled. So that is the time to adjust the flow. So how much flow has to be adjusted on that shortest augmenting path is the amount indicated by the sink's first label. Okay. So how to adjust the flow is the augmentation of the current flow is performed along the augmenting path traced by following the vertex of the second labels from sink to source. That is how to adjust the flow on that thing is you have some augmenting path, no? So you have to start from this sink up to the source. You have to look up what is the second label from sink to source. The current flow quantities are increased on the forward edges and decrease the current flow on backward edges. Okay, so we'll discuss with one example. Okay, once if you are continuing the labeling process, once if we have labeled the sink, stop the labeling process. Then you have to adjust the flow on that augmenting path. You start from this sink. Okay, how much flow you have to increase on that path is always the sink's first label. Okay, so if it is a forward edge, you have to increase the current flow on that flow value. If it is a backward edge, you have to decrease the current flow by that much unit. So once again, if the sink remains unlabeled after the traversal Q becomes empty, the algorithm returns the current flow as the maximum and stop the algorithm. So this is the pseudocode what we have discussed, which is given as this. Okay. So initially, first you have to assign xij equal to 0 to every wedge. Okay. So in the graph, they were given only the capacity. So you have to assign the current flow on all the edges of the graph as 0. Okay, then initially you have to label the source with infinity comma minus, add the source to empty queue. Okay, so if the queue is not empty, okay, you remove the first vertex in that queue. Okay, for every edge from I to j. So where I is nothing but the edge, vertex which you are removed from the queue. from that vertex, whatever the vertices that can be reached from I, forward edge, you have to label all the forward edge. Whatever the vertex you are labeling, you put it into the queue. So once if you labeled all the forward edges from that vertex I, then you have to go back to labeling the backward edges. Okay. Is there any backward edge from J to I? Again you label all the backward edges. Okay. Again you add that vertex into the queue. Okay. So once if you have completed for labeling the forward edge and labeling the backward edge, then you have to check whether if the sink has been labeled. So what I said, if the sink has been labeled, it's time to augment the flow. So augment along the augmenting path. Okay. So as I said, you have to start from the sink. Okay. That is J equal to N. Start at the sink and move backward using the second label of that each and every vertex. Okay. So if the second label of the vertex is plus, okay, you have to increment the current flow by that flow. Always the flow may be the sink's first label. If it is a backward edge, you decrement the current flow. Okay, again you will move on to the next vertex on the second label. This process has to be repeated until you reach the source. Okay. So once if you have adjusted the flow on that path, you have to erase all the vertex labels except the ones of the source. Again you reinitialize the queue with source. Okay. So if there is no more element, okay, on that queue, then which means that if you couldn't able to find the shortest augmenting path from source to sink, okay, in that case the algorithm is terminated. So you consider this is a one example of a flow network. We are supposed to find out what is the maximum flow in this network. Okay. There are 6 nodes. Source one is the source vertex, sink is the 6. Okay. So these are all the capacity. These are all the capacity. So initially, first step is you have to initialize the current flow on all these edges as 0. That is, you have to initialize 0 bar 2, 0 bar 3, 0 bar 5, 0 bar 3, like this. So what is this 0 indicates here as current flow. This 2 indicates capacity. So the current flow, what we say, this is an Xij. So whereas the 2 is nothing but the Uij. So this is current flow Xij. This 2 is nothing but the Uij, that is capacity. Okay. So initially in the problem you will have only the capacity. The first step you have to initialize all the edges like this. Current flow bar capacity. Initially the current flow is 0. So this is what we have assigned for all the edges. The current flow was 0. So we are supposed to start our labeling process. Okay. So first you have to label source with infinity comma minus. Whatever the vertex you are labeling, you have to put it into that queue. Okay. So this is already given. Now we will start with the new queue steps. Okay. First we are adding 1 to the queue. Okay. So what is the second step? Once you have labeled the source vertex with infinity comma hyphen, okay, you put the vertex into queue. Okay. What is the next step? You have to forward the label the forward edge. Next you have to label the backward edge. Okay, that is the thing. Then next you have to check whether the sink has been labeled. Okay, if so, you find the augmenting path, adjust the flow, you repeat the process until there are no more augmenting path between source and sink. Okay, listen. So the vertex 2 has not been initially labeled. Okay. So this is that final graph after completing all the process. Okay. So here, look at here, the 2 is not labeled since it is a forward edge. Okay. So in order to label this, what you are supposed to do, you have to subtract the capacity minus current flow. That is 2 minus 0. 2 minus 0. So which is equal to 2. So you have to label with this Rij or Li. So this is I know. From 1 to 2 only you are finding. So what is this first label value? Infinity. So if you compare these two, 2 with infinity, which is minimum 2. So that's why you are labeling the vertex. The first part of the vertex label is 2. This is nothing but how much flow that can be adjusted. To find that, you subtract these two, capacity minus current flow. You compare this flow with the current flow of this vertex I. Okay, that is in our case 1. Infinity and 2. 2 is minimum. So the first part of the label is 2, comma. The next part of the label is what it indicates, from which the vertex was reached. If it is a forward, you label with plus. Okay, because 2 is reached from 1. So that 1, since it is a forward edge, so that plus. So the 2 is labeled with 2 comma 1 plus. So now what is the vertex you have labeled 2? So you put the vertex into Q. This arrow indicates that the vertex was removed from the Q. Okay, the arrow here indicates that these are all the vertices which have been removed from the Q. Okay. So you have to first label all the forward edges from 1. Okay. So the next forward is 4. Okay. So 3 minus 0, 3. Then what is the label of this? Infinity, which is minimum 3. So you label 3, comma. Again the 4 is reached from 1. So 3, comma 1. Since it is a forward edge, plus. So now what is the vertex? So you have labeled 4. So you put that vertex also into Q. Okay. So you have labeled all the forward edge, that is 1 to 2, 1 to 4. For 1 there is no backward edge, because of 1 there is no vertex before that of, because since no incoming edges. So there is no backward edge. Okay. Then you check whether the Q is empty. No. And also the sink has not been labeled. Okay, so again you have to continue the labeling process. So what is the next vertex in the Q? 2. So you remove 2 from Q. You have to start the labeling from the vertex 2. Listen. So there are two forward edges for 2. One is 2 to 5, another one is 2 to 3. So usually we'll go into the chronological order. Either you can label 5 or you can label 3. Doesn't matter. So first we label with 3. Okay. So 5 minus 0, 5. Okay. Now listen. Since 3 is reached from 2. Okay. So 5 minus 0, 5. What is the flow of this network? Vertex. 2. Okay. So this is ith vertex. This is J. So you are labeling this jth vertex 3. Okay. So you have to compare Rij, that is 5 minus 0, that is 5. This value to be compared with Li. What is the Li? 2. So whichever is minimum, 2. So that's why 3 first label part is 2. Okay. The next part of the label indicates from which vertex it is reached. So 3 is reached from 2. So 2 comma 2. Since it is a forward edge, you label with plus. So now what is the vertex you have labeled 3? So that add it into the Q. Okay. The next, there are one more forward edge 5. So 3 minus 0, 3. Then you compare this label 2, which is minimum again 2. So 2 comma, again 5 is reached from 2. So 2 comma 2. Since it is a forward edge, plus. Now what is the vertex you have labeled? 5. You add that vertex also into Q. Okay. So now you have to go for labeling the backward edge. Listen. So 2, there is a 1 backward, that is 1. But the vertex has been already labeled. For all the unlabeled vertex only you have to do the process. Okay. So for 2 there is a 1 backward edge, that is 2 to 1. But the 1 has been already labeled. Okay. So from 2 you have labeled all the forward edges and as well as backward edges. Then you check whether the sink has been labeled. No. and also the queue is not empty. So you remove the next vertex from the queue, then you start the labeling process. So what is the next vertex you have to remove from the queue is 4. So from 4 you are supposed to label. Okay. So the one forward edge is 4 to 3. But 3 has been already labeled. So whatever the vertex we have labeled, we put it to the queue now. So 3 has been already labeled. Okay. And for 4, there is a one backward edge, that is 4 to 1. 1 is also labeled. So leave it. Okay. Then you check whether the sync has been labeled. No. And also the queue is not empty. So next you remove the next vertex from the queue, then start the labeling process. So the next vertex what we are looking is 3. So from 3 you have to label. Okay. So there is a one forward edge 3 to 6. Okay. 2 minus 0, 2. What is its label? 2. Which is minimum? 2. Both the values are equal. So 2 comma. Which vertex the 6 is reached? 3. So 2 comma 3. Since it is a forward edge, you label with plus. So 6 is labeled with 2 comma 3 plus. Then you add that vertex is also Q. Whether it is a sync or source doesn't matter. Whatever the vertex you are labeling, you put the vertex into Q. That is, you add it into the Q. Then is there any forward edge? No. Then you check whether is there any backward edge. Yes. 3 to 2 and 3 to 4. But both the vertices are already labeled. Okay. So you labeled the forward edge and the backward edge. Then you see to that whether the vertex sync has been labeled. Yes. Sync has been labeled. At that time you stop all the labeling process. It's the time to augmenting the flow. Okay. Before augmenting the flow, you have to find out the shortest augmenting path. Okay. So because there are so many paths are available, you have to find the shortest augmenting path. Listen, I'll tell you how to find that. So we have to start with this node sync. Okay. 6. What is its second label? You look at the second label, 3. Okay, you have to come here. What is its second label? 2. Come here. What is its second label? 1. Okay, so this is what this shortest augmenting path, that is 1 to 2, 2 to 3 and 3 to 6, since all are forward. Okay, once again repeat. Look at the second label 3. Look at its second label 2. Look at its second label 1. You reached the sync. So the augmenting path is 1 to 2, 2 to 3 and 3 to 6. You will have this one more path also. That is 1 irko. But doesn't matter that. Okay. You cannot have this. That is 1 to 4 or 4 to 3 to 6 or 1 to 2 to 5 to 6 also. Among these, this is going to be the shortest augmenting path. Okay. So once if you find out the augmenting path, you have to adjust the flow on that path. Okay. How to adjust the flow is, again you have to come back on the backtracking only. Okay. How much flow has to be increased in the sense, always the sync first label. So here the sync's first label is 2. Okay. Sync's first label, that much flow has to be increased in case of forward edge. That much flow has to be decreased if it is an backward edge. So the current flow has to be increased or decreased as 2 since the sync's first label. Okay, augment the flow by 2, the sync's first label along the path 1 to 2, 2 to 3, 3 to 6. Okay, listen. So again you have to start back only. Okay, so 3 to 6. So this is a forward edge now because you labeled it as a plus. Okay, so how much flow you have to increase? 2. What is the current flow? 0. So you have to increase the current flow by 2 units. That is 0 plus 2, 2. I'll show it in the next slide. What is that graph? So you have to increase the current flow by 2. Don't alter the capacity. Okay. The next, what is its second label? 2. No, you come here. So what is the current flow? 0. Again, this has been labeled with plus. It is a forward. So you increase that current flow by 2 units. So 0 plus 2 is 2. Again, you come back. The second label is 1. Since it is a plus, 0 plus 2, 2. So on this path, you have added 2. See, initially it was 0. On this path 1 to 2, 3 to 6, the current flow has been increased as 2. Okay. So the next, again, you have to continue the same process. First, you have to label the queue. Sorry, label the source. Okay, label the source as infinity, comma, hyphen. You put the vertex into the queue. You remove that vertex from the queue also. Start labeling. The same process. Where you have to stop that iteration in the sense, you couldn't find an augmenting path from source to destination. Okay. So again, there are two forward edges, 1 to 2 and 1 to 4. Listen carefully. When you try to label 2, since it is a forward edge, you have to find only the residual, isn't it? How to find the residual? Capacity minus current flow. So that is 2 minus 2 is 0. So which means that the capacity of this edge is 2. The current flow is also 2. So what I said, the constraint, you cannot carry apart from this capacity thing. Okay. So you cannot exceed the capacity. So we have adjusted the flow on that path. Okay. So that you cannot label 2 as of now. Okay. Since if it is, the residual is greater than 0, then only you can able to label. Okay. So you cannot label now 2. Next you can label 4. Okay. So 3 minus 0 was 3. Okay. So what is its current label value? Infinity, which is minimum 3. So 3, comma, which vertex 4 is reached? From 1. So 3, comma 1, since it is a forward, you label it as plus. So what is the vertex you have labeled now? 4. That you add into Q. Okay. The next you check it for 1, there is no backward. Okay. Again, you have labeled sink. No. What is the next? Whether the Q is also not empty. What is the next vertex in the Q is 4. You remove that vertex from Q. Then you start labeling from the vertex 4. So from 4 there is only one forward edge 3. Okay. So 1 minus 0 1. What is its label? 3. So which is minimum? 1. So that you label the vertex 3 with 1 comma 3 is reached from 4. So that is 4 since it is a forward plus. What is the vertex you have labeled? 3. So you add that vertex into Q. Okay. Again for 4 there is a backward edge but 1 is already labeled. Again the sink is not labeled. Okay. The Q is also not empty. So you remove the next vertex from the Q is 3. So you start labeling from 3. First always you have to label forward edge. Then only you have to come to backward. So from 3, 1 forward edge 3 to 6. But again this residual 2 comma 2 is 0. So you cannot adjust the flow. So you cannot label 6 as of now. Leave. Then you come to the backward. For 3 there are 2 backward. One is 3 to 2 and another one is 3 to 4. But 4 has been already labeled. So you have to label 2. So because 2 is not already labeled. Listen. For labeling the backward edge, you have to consider only the current flow on that edge. So what is that current flow? 2. Because 2 is reached backward from 3. Okay. What is its label value? 1. So you have to compare 2 comma 1. So once again I'll repeat. You are labeling 2 since it is a backward. Okay. Don't subtract 5 minus 2. You consider only this current flow, that is 2. This value to be compared with the current flow of this. Okay. That is 1, which is minimum 1. That's why 2 is labeled with 1, comma, from which vertex the 2 is reached by backward? 3. So 1 comma 3. Since it is a backward edge, you label with minus. 1 comma 3 minus. So what is the vertex which we have labeled now? 2. So you add that into Q. So you add 2 to Q. Okay. Next you check whether the sink has been labeled. No. Whether the Q is empty? No. What is the next vertex from the Q is 2. So you remove the vertex. From 2 you start labeling. Okay. So again for 2 there is 2 forward edge. One is 2 to 5 and another one is 2 to 3. But 3 has been already labeled. Okay. So you cannot do anything. Okay. So you label 5. Since it is a forward, no. So 3 minus 0, 3. What is its label value? 1, which is minimum 1. So that is 1, comma. Again 5 is reached from 2. So 1, comma 2. Since it is a forward, plus. What is the vertex we have labeled now? 5. So you put the vertex into Q. Then you check for the backward edge. Yes, 1. But it has been already labeled. The sink is not labeled as of now. Again the Q is not empty. So you remove the next vertex from the Q, 5, you start labeling. So from 5 there is only one forward edge, 5 to 6. So 4, 0 is 4. What is its current label? 1, which is minimum 1. So 1, 6 is reached from 5. So that is 1, 5. Since it is a forward, plus. What is the vertex you have labeled? 6. Then you label backward. There is only one backward for 5 too, but it is already labeled. Then you check whether the sink has been labeled. Yes, sink has been labeled. So you stop the labeling process, then find the augmenting path, adjust the flow. Okay, listen carefully. So again, in order to adjust the flow, first you have to look at this starting at the sink. So the flow has to be adjusted on that augmenting path is 1. Because 1 is the sink's first label. Always whatever the value which has given in the sink's first label, that much unit has to be increased or decreased. Okay. How to find this augmenting path in the sense? Again you traverse backward by look at the second label. Starting from sink. What is its second label? 5. So you come over here. 5. Okay. What is the edge for plus? Since it is a forward edge, you have to increase the current flow by 1. That is 1, 4. Okay. Then once if you come to 5, what is its second label? 2. Since it is a plus, no. So again this current flow has to be increased by 1. That is 1, 1 bar 3. Again what is its second label? 2. So you will come over here. 2. Okay. So now you look at this. This is labeled with what? Minus. This vertex is labeled with minus. 2 தான் reach ஆயிட்டிருக்கும். Here it is labeled with minus. So that on this edge, okay, you have to decrease this current flow by 1 unit. You have to decrease this current flow by 1 unit. So 2 minus 1, 1. Okay. Since this is labeled with minus, I have told backward edge means you have to decrease the current flow. So you have decreased the current flow by 1. Then what is its second label? 3. So you will come over here. Okay. So what is its current label? Sorry, second label? 4. So you will come over here because this vertex is labeled with plus. So this edge has to be increased by 1 unit. 1, 1. Again, what is its second label? 1. So you will reach to the sink. It is also labeled with plus. So you have to increase the current flow. So the augmenting path is 1 to 4, 4 to 3, but 3 to 2 is backward. Then 2 to 5, 5 to 6. That's what they have given. 1 to 4, 4 to 3, 3 to 2 is backward. Again 2 to 5, 5 to 6. So 5 to 6 increase the current flow. 2 to 5 also increase the current flow. But between 2 to 3 you have to decrease the flow. 4 to 3 increase. 1 to 4 also increase. I'll show the graph in the next. See, in this path also the flow is increased. Here also increased. Here decreased. Here also increased. Here also increased. Okay. So this is that after the second iteration. So again you have to do that when you have to stop when you couldn't find an augmenting path. So again you reinitialize the queue by adding the source vertex. Okay, label source with infinity comma hyphen. Label the forward since 2 cannot be labeled because 2 minus 2 0, that is it has been flow is adjust. Then one can come to the forward edge 4. 3 minus 1 is 2. What is its current label? Infinity, which is minimum 2. So 2 comma 1 plus. So you add that vertex 4 into Q. For 1 there is no backward edge. Sink has been not been labeled. Q is also not empty. You try to label the vertex from 4. 1 forward edge 4 to 3. But you look at this. 1 minus 1 is again 0. There is no residual. Okay, which means that the flow is adjusted on that path. Okay, so you cannot label 3. So for 4 you look at any backward edge. Yes, but 1 has been already labeled. Okay, so sink has not been labeled, but here the queue is empty. There are no vertices to label, which means that at this point you couldn't able to find the shortest augmenting path from source to sink. So you stop the iteration. Okay, so that current solution whatever you have obtained, that is going to be the optimal solution. That is the concept of iterative improvement. Now you start with some initial basic solution, you make some changes on that next iteration and so on. If you couldn't able to modify that changes, okay, you stop that iteration. The last or the recent feasible solution may be the optimal solution. So here what is the change we are making is every time you are finding the augmenting path, adjusting the flow. When you couldn't find an augmenting path from source to sink, stop the iteration. Then we are supposed to find out what is the maximum flow that can be sent on this network. So in order to find that, you need to see that what is the cut. Okay. So we'll denote that cut may be this C of x comma x bar. Okay. What it is meant as a cut will have some set of edges. Okay. If all the edges in that cut, if you remove those edges, if you couldn't find an path from source to vertex, okay, cut will have some set of edges. No, if you cut those edges, which means that you couldn't able to reach from source to sink. If all the edges of a cut were deleted from the network, there would be a no directed path from source to sink. Okay, so you have to find such an edges. Okay, so that if you remove all those edges, you could not able to reach from source to sink. Those kind of edges we will call it as an cut. What is a minimum cut is? A minimum cut is a cut of the smallest capacity in a given network. The cut which is having the minimum capacity. Cut of the smallest capacity in a given network. So here there are 3 cuts. So listen, C of x comma x bar is equal to 1 comma 2, 1 comma 4. See, if you remove these edges, you are removing 1 to 2 edge and as well as 1 comma 4. From this graph, can you able to reach from 1 to 6? No, it is not possible because in order to reach 6, either you can come via 2 or 4 from 1. Then only you can able to reach 6. So if you remove these two edges, you could not able to find a path from source to sink. So that is the one cut. So the cut will have, cut is nothing but set of edges 1 comma 2 and 1 comma 4. So what is that capacity of this cut is? You add the capacity on these edges 1 comma 2 and 1 comma 4. What is the capacity of this edge? 2. What is the capacity of this edge? 3. So 2 plus 3 is 5. The next cut is 3 comma 6, 5 comma 6. That is this. Another cut. If you remove these two edges also, you cannot able to. You have this edge. Only you are removing these two edges. Again, you cannot find a path from source to sink. So this is another cut. What is the capacity? 4 plus 2 is 6. Okay. Then there may be more than one cut. Okay, the another cut is 2, 3, 2, 5, 4, 3. So that is this one. 2, 3, 2, 5, and another one is 4, 3. If you cut all these edges together, if you couldn't remove any one of this edge also, still you can find. Suppose if you are removing these two edges alone, you can reach 1 to 2, 2 to 5, 5 to 6. If you didn't cut these vertex, edge, you can reach 1 to 4, 4 to 3, 3 to 6. Again, if you couldn't remove this, you can go this way or this way. But if you are all together, if you are removing all three edges, then there won't be any path from source to sink. So the another cut is 2, 3, 2, 5, 4, 3. You add all these capacity. So 3 plus 5, 5 plus 1 is 9. Okay. So how to find the maximum flow that can be sent on this? A cut which is having the minimum capacity, that is having an maximum flow. So which among these three cuts, which is having the minimum capacity, that is 5, no, that could be a maximum flow. So the maximum flow that can be sent on this network may be this 5. This is called as a Maxflow mean cut theorem. The value of a maximum flow in a network is equal to the capacity of its minimum cut. Okay, so the maximum flow can be passed on to that network as 5, because that min cut is having the capacity as 5. Okay, so the shortest augmenting path algorithm yields both a maximum flow and a minimum cut. Okay, so the maximum flow is the final flow produced by that algorithm. So the minimum cut is formed by all the edges from the labeled vertices to unlabeled vertices of the last iteration of this algorithm. Okay. So if all the edges from the labeled to unlabeled vertices are full, that is their flow amount are equal to the edge capacities, while all the edges from the unlabeled to labeled vertices, if any, have zero flow amounts on them. Max flow mean cut theorem. So in order to find out what is the maximum flow, you have to find out the mean cut. So the cut which is having the minimum capacity, that is going to be the maximum flow. Coming to this time efficiency. So first you have to find the shortest augmenting path now by applying this BFS search. So that is big O of n plus m, which is equal to big O of m adjacency list. Okay, the number of vertices. Okay, the total time efficiency of the shortest path is big O of n into m square for this representation. But you have some more efficient algorithm, that is big O of n into n time, but which is not comes under this iterative improvement technique. Thank you.